Hello, everyone, and welcome to the Best Paper section. My name is Rita Borgo, and on behalf of the full papers chairs, Liz Marai and Tatiana von Landersberg, I will be leading part of this special session. And for you, we have two very exciting talks today. These are the papers that were chosen by the Best Paper Committee from 5 main nominations. And we thank the Best Paper Committee, which consists of Roxana Buyak, Tim Dwyer, and Kay Nielsen. And we should have already been announced that the Best Paper Award this year went to color nameability. The author are Khairi, Reda, and Salvi, Jack Ray, and Michael Papka. And this would also be the first papers that will be presented. So I'm happy to leave the stage to the presentation of our first best paper.
My name is Khairi Reda, and I'm going to be presenting our work on how color nameability predicts inference accuracy in spatial visualizations. Now, color is a foundational visual property that's often used for communicating quantitative information, and particularly in spatial visualizations, such as the ones in these examples. Now, these representations are often used for communicating critical scientific data, so it's equally important for us to find effective color design principles that maximize viewers' interpretation of these data sets. Now, of course, this is a question that the visualization community has grappled with for a long time, and the community has devised a number of guidelines to ensure effective color designs. Often these guidelines emphasize perceptual factors such as perceptual uniformity and discriminability to ensure that the distances between colors are both equal and large enough. But we also know that colors do evoke other higher level cognitive associations, including semantic and linguistic associations, which are naturally activated when we look at and think about color. Now, these factors have been leveraged and have been used to facilitate the encoding of categorical data, but their role in interpreting quantitative information is still not properly understood. And in this work, we're focusing on color names. In particular, the question that we're asking is how important are color names to the interpretation of quantitative visualizations, such as the map in this picture. Now, in asking this question, we also want to move beyond value retrieval tasks that are typically used in these studies. So instead of perhaps asking observers to estimate the value associated with a particular color, we want to utilize slightly more complex tasks. So we're using graphical inference as a model task for this. And in this case, we're showing observers a series of plots that are sampled from different models, and we're asking participants to identify the plot that's associated with a unique or an outlying model. And in this case, that would be the one that's highlighted here. Now, this task is slightly more complex because not only involves comparison, but it also requires viewers to make an inference about the models that underlie a set of visualizations, rather than directly reading values that are associated with colors. Now, we've actually run this study a year ago, and what we found out is that accuracy is indeed correlated with color name variation. So color maps that blend a variety of names led to better inference performance. And in this case, we see a better performance for rainbow color maps, which blend a variety of names as compared with more traditional designs, such as the Veritas color maps. Now, the limitation of that study is that color name variation, which is the metric that we've used, was very much correlated with perceptual distance, as measured in the lab space. So it wasn't really very clear which of these two factors was responsible for the improved performance. And this is a question that's important to answer, because if we're hoping to devise guidelines, we should be able to tell designers whether to optimize for nameability, or whether it's sufficient to only consider perceptual distances and the differences between colors as measured in a perceptual color space, such as a lab. But then we had another insight when we dug further into the results, and as it turned out, the most accurate color map in that experiment was a traditional RGB rainbow, which is interesting not only because this design is thought to be ineffective, but also the traditional rainbow outperformed an improved version called Turbo that is meant to be a replacement designed by Google engineers. And so one hunch was that it wasn't necessarily just the number of colors, but also the nature of those colors. So if we take the yellow in a traditional rainbow, and then we try to visualize the names that are associated with this color, what we find out is that most people agree on the name, and then essentially describe it either as bright yellow or as plain yellow. By contrast, the yellow in Turbo involves a much wider distribution of names, including yellow, mustard, and even strange names such as puke. Now, this also happens with green. We see a much narrower distribution with a traditional rainbow of greens, and a much more diffuse distribution of names for the green in a Turbo color map. And so natural question is whether using these more common names at the top can actually facilitate inference. And as it turned out, there's actually a quantitative metric that captures this tendency very well. Color name saliency, which has been proposed by Here and Stone, quantifies the level to which a color is associated with a unique and salient names. So to illustrate this, if we take two slices of the lab color space, we're coloring the points here by the saliency of those colors. So the bigger the colors, the more salient the names associated with them. And so if we cleave this color system and then we leave out only the most salient names, we're left with the traditional colors that we typically refer to as basic colors, such as green, red, brown, blue, and yellow. Now with this information, we can find a color map such as Jet that's primarily composed of basic color names. Now if we try to measure the name saliency at different levels of the color scale, and then measuring or averaging those measurements, we get about 57% name saliency for this entire color map. We can then obtain an almost perceptually equivalent version, Turbo, except that the main difference between these two is in their name saliency. Now indeed, if we try to plot perceptual discriminability here on the x-axis for these two color maps and against name saliency, what we'll find is that both of these color maps have very similar perceptual qualities, with the main gap being in their name saliency. Now we can also find another pair of color maps, such as purple-pink, which enjoys relatively high name saliency, and compare that to teal-beige, which is a very much perceptually equivalent color map, but with colors that are empirically less salient. Similarly, we have gray-red here, names that are relatively more salient compared to teal-brown with less salient names, but almost equivalent perceptual properties. So we take these 6 color maps and then we use them for this next study. Now, we also have to consider how many color names there are in a particular scale. And for this, we used a color name variation metric that we've proposed in earlier work. And to illustrate how to do this, how to calculate this metric, we take every pair of adjacent colors, and then we compute the probability that they're associated with different names. And so to illustrate, taking these two blues, it's very likely that people will almost give them the same name. So the probability here is very low that they're given distinct and unique names. By contrast, if we take green and yellow, it's virtually impossible for people to confuse them and give them the same name, so probability is very high here. Now, if we sum up these measurements, we get an overall color name variation for each color map. So for Jet, this stands to be about 4.9. For Turbo, this is almost very similar, so we get about 5.1 color names. Now, if we take our two divergent color maps, gray, red, teal, brown, they're also similar in terms of name variation, but they're also less than rainbow color maps, which would make sense. Going back further down, we take purple, pink, and teal, beige, and then we also compute their color name variation, and then we also get a lower measurement overall. Now with these two metrics, color name saliency and variation, we can define two hypotheses. The first hypothesis is that colors endowed with more salient names will facilitate more accurate interpretation. So if we take our color maps with high name saliency here on the left, we expect them to perform higher than the group here on the right. even though the pairs here between the two groups share almost very similar perceptual qualities. Now, the second hypothesis is that nameability, which is a combination of saliency and name variation, will collectively provide a better explanation of participants' performance than perceptual discriminability alone. Now, in order to test this hypothesis, we developed two models, a nameability model that's trained with two predictors, and a perceptual model that's solely based on perceptual discriminability in the lab space. And we compare these two models, and then we see which one wins. Now, for our first experiment, we also use this graphical inference task that I've introduced before. We show participants choroplasts that are sampled from different models, and then we ask them to identify the plots that does not seem to belong. In addition to choroplasts, we also tested smooth geographical maps, which are very similar, but the only difference is that they data here very smoothly, versus in the choroplasts, it's aggregated county by county. But to give you a sense of how these stimuli are generated, we start with a target model that is composed of a number of kernels, Gaussian kernels. These kernels are distributed and rotated randomly within the 2D domain for every trial. We take the target, we perturb it to a certain extent, and we obtain an equivalent decoy model. We sample the target once, and that would be the plot that's the correct answer. We sample the decoy 3 times and embed them all into one lineup. Now, in addition to the variation between the target and the decoy, there's also variations between the decoys among themselves. So that sort of makes for a little bit more interpretive task where the viewer would have to differentiate features that are truly model differentiating from those other visual features that might have arisen by purely by chance due to the random sampling process. Now, looking at the accuracy results, we do see a significant effect for name saliency. And in particular, color maps that have highly salient names tend to outperform the color maps that have lower name saliency, even though the difference between these two groups in terms of perceptual discriminability is almost negligible. So, for example, we see a difference between jet and turbo in favor of jet. We also sometimes see a difference between gray-red, teal-brown, and also between purple-pink and teal-beige. Now, if we explicitly plot the difference between the high and low saliency color maps, we do see generally a non-zero advantage, and particularly in smooth maps. The advantage seems a little bit less in choroplasts, where the CIs do intersect slightly with 0, although the differences between these two visualizations were non-significant in formal modeling, and name saliency had a significant effect across the two conditions. And so the second question is whether these performance differences can indeed be explained solely by perception. And for this, we compare the two models, the nameability and the perceptual model, and we use the AIC criterion to judge which of these models is a better fit. And in this particular case, we get a significantly better fit with the nameability model. The difference in fit was significant even after penalizing the nameability model because of its larger complexity. Overall, the nameability model is 36 times more likely than the perceptual model, considering the empirical data that we have gotten from the experiment. So in summary, what we find is that visualizations with more prototypical and more salient color names tend to facilitate better graphical inference. So overall, we get about a 10% boost in accuracy just for using colors with more salient and prototypical names. These effects could not be attributed to perception alone, based on the comparison between the two models. However, the advantage for name saliency may be slightly weaker in choroplasts than in a smooth representation. Now, these effects were not sort of significant, so we didn't find, again, a significant difference between the smooth maps and the choroplasts. But this is something that's worthy of investigating. So we've designed a second experiment. We wanted to replicate the results. This time we're using discrete heat maps versus scalar fields, which are smoother and vary more continuously. Now, the difference with heat maps as opposed to choroplasts is that the boundaries or the bins are much more uniform here as opposed to the geographical boundaries in a choropleth, which are sort of more or less jagged and less uniform. And again, the experiment here where participants in the experiment were asked to essentially differentiate the plot that belongs to an incompatible model. Now, looking at the results, again, we do see an effect for name saliency. So the more salient color names tend to perform better than perceptual equivalent low saliency names. Looking at the difference between the two, we do see a non-zero difference in both representations, in both scalar fields as well as heat maps. Now, comparing the nameability and the perceptual models, we do see a substantially better fit with the nameability model, which supports H2, but also suggests that the effects that we've seen here are likely attributable to color names rather than to perceptual differences between the colors that we've tested. So in summary, in trying to summarize the results from the two experiments, we find that language does play an important role in interpreting color-coded data. Color names may in fact be more important for graphical inference than perceptual discriminability, as evidenced by the comparison between the two models. As guidance, we can suggest colors that people can name more reliably, example, colors with more basic terms. So for instance, yellow is better than beige, blue is better than teal. We also found that scales with more varied color names, which at the same time leads to higher perceptual discriminability, these two factors lead to overall better graphical inference. So overall, we find that rainbows tend to outperform divergent color maps. Divergent color maps, in this case, tend to outperform also multi-hue or single-hue color maps, which tend to have lower number of names. So of course, the central question here is, why do color name matters in quantitative data where there's no obvious linguistic associations? Well, one idea is that color names do allow selective attention to features within the data. So for instance, I can refer to red hotspots, yellow rings, or green halos, and these names that are attached to colors may provide vocabulary to describe these features, not only in communication, but also for somebody's own problem solving. So they may facilitate attentions to features that are otherwise too fuzzy to be described or to be thought about. But they also may allow more sophisticated qualitative assessments. So I can perhaps compare these two images, and I can say that the image on the left, or the image on the right here in this case, exhibits more blue than the image on the left. And these kinds of qualitative assessments are facilitated by color names. And we think that maybe is the reason why a lot of practitioners still continue to prefer colorful maps, such as a rainbow, even though these color maps may come with their own perceptual difficulties. The fact that names do provide a benefit in this case may outweigh the perceptual problems that these color maps tend to produce sometimes. The limitations of this work is that we've only considered, of course, graphical perception. So the question is, what about other tasks? Can color maps be useful, or can color names be useful in other situations? And in particular, one may want to consider categorization, which is sort of reinforced by color names, versus the perceptual precision that may be lost or gained as a result of using more nameable colors. Now, the second question that we want to consider for future work is whether we can design new color maps that balance nameability with traditional perceptual properties. So there are examples for generating categorical palettes, such as Colorgorical, which allows us to balance a number of constraints, including both nameability and perceptual factors. So it would be interesting to see whether these tools can be extended to generate quantitative encodings, in addition to being able to generate categorical palettes. So with that, I would like to thank you for your attention, and I'd be happy to take any questions that you may have.
Thank you, Khairi, for your presentation. So we already have a question, and actually I invite all the viewers and attendees to please post question on Discord or on the YouTube chat. The first one is from Tim Gerritz, and he's asking, I imagine that color nameability is highly reliant on the language and region. Did you also look into that?
So that's a good point, actually. There's definitely differences across languages between how different cultures name colors. We haven't looked into that linguistic or cultural variation in this experiment. I would say that most languages do have names for the basic colors like red, green, yellow. Those names tend to be like cross-cultural. There's evidence for that, and they also tend to be very salient. So we would expect those colors to sort of result in similar performance across different languages, although we haven't really looked into that in this work. So that's a very good question for future work.
Thank you. So we have another question, which is from Wolfgang Heimann. Regarding green halos and red hotspots, isn't the risk here that we identify regions that artificially appear as a result of the color mapping process and do not have anything to do with the patterns or the features of the data?
Yeah, so this is another good point that people have hypothesized that there might be an issue of due to categorization, and there may be some artifacts that we may accidentally identify, or versus those artifacts may not actually be sort of abrupt switches in the data. That's a good point. We have, in this experiment, we haven't really looked into that effect, sort of the effect of, let's say, false positives. We've done work in the last year where we specifically looked at whether categorization would increase the risk of false discovery, for example, in the context of graphical inference. We didn't find evidence for that. That's still a plausible hypothesis that should be investigated. But we haven't looked into it specifically in this work. We were mostly looking at the accuracy, or let's say the discriminability between different models. That being said, yes, there's a potential chance that we might be over discriminating if we use a lot of categories of colors.
Perfect. Thank you for your detailed answer. We have one more question from Karsten Rink. And the question is, after years of everyone telling me I mustn't use rainbow color maps, apparently they're not that bad. So is there a rule of thumb when rainbow should be used and when it shouldn't?
So I think rainbows can still be disadvantageous in certain situations, especially if you're trying to communicate to a broader audience, for example. We know that it's going to be pretty difficult for people with color vision deficiencies to see all the spectrum of colors in rainbows. So when that is concerned, rainbows or traditional rainbows should not be used. But there's other rules that we can sort of come up with, and those are, for example, we could instead of using colors that are less nameable, maybe try to use colors that are that have more salient or more prototypical names, like red, pure red, or pure yellow, or pure blue. Those tend to perform better according to our experiments. So even though we're not encouraging everybody to use rainbows in all situations, if you can replace your colors with ones that have more salient or more prototypical names, you might get a performance boost, especially in tasks that require sort of inference and thinking about features and their association with color names.
Thank you. And unfortunately, we have only time for one more question. So this will be the last question, but I encourage the discussion to progress on Discord, because I do think that this is quite a interesting and challenging topic. So it would be very interesting to see the discussion to progress even during the conference. So the last question is from Thomas Schultz. And he's asking, in this task, rainbow color maps visually indicate isocontours of the probability distributions. These seem to provide very reliable cues to identify the outliers. I wonder how well people would do with isocontours alone and without any colors.
Yeah, that's a good question. That's actually could be a very interesting follow-up study with similar format, whether, just using traditional color maps, but sort of adding ISO contours on top of that, would people get the same performance benefit that we were seeing in rainbows? That is indeed a very interesting, sort of proposition. So obviously we haven't done it in this study, but I would speculate that you might get this performance boost, whether it's the same as we would get with the more salient color names. That's a question remains to be answered. But this is actually a very interesting question that could be investigated in the future. So thank you for that.
Brilliant. Unfortunately, due to time, we need to move on to the next talk, but let us thank again our speakers, and thank you and congratulations for your involvement.
Thank you very much.
Okay, I think I seem to have disappeared. So what I was mentioning is that the paper that is following is another work that stood out from the pool of paper, and it deserved an honorable mention. And the award, the honorable mention award this year went to what are table cartograms good for anyway, an algebraic analysis. And the paper is from M McNutt. The paper proposes algebraic visualization analysis as a way to evaluate the effectiveness of visualizations, and it brings rigor to the problem of appraising effectiveness of specific visualization technique against task. So we would like to leave the stage to Andrew McNutt, who will present his amazing work.
Hello, my name is Andrew McNutt, and today I'm going to be talking about my paper, What Are Table Cartograms Good For Anyway? In Algebraic Analysis. An important question in visualization is how do we know when a visualization is good? There are a lot of ways to answer this, ranging from Tuftian ideas like adherence to a set of design principles to Jock McInlay's ideas of effectiveness and expressiveness, and a whole host of others. A somewhat rarer, but still important question is how do we know what a particular visual form is good for? What tasks can a bar chart do? What data is appropriate for a scatter plot? These are important questions to answer, as knowledge of the functional attributes of a visualization's form should ideally motivate its usage. Luckily, years of practice tend to be good guides for usage, and many forms of visualization have been around for centuries, and thus their properties are well understood. But what about new, novel, or unknown visualizations? Few previous techniques help us understand such forms in an easy or economical way. A common mechanism for understanding how to use a chart form is by looking up relevant guidelines. This can be an effective way to understand best practices. However, guidelines are often bound to particular chart forms, which precludes their use on novel entities. In contrast, user studies are able to address questions for any chart form, new or old, and therein provide real concrete scientific evidence about how a chart might be most effectively used. Unfortunately, these can be slow, costly, and difficult to execute. In the spirit of discount usability studies, a potential solve might be to use a theory-based analysis to generate guidelines. Yet, using theory for evaluation can be a mixed bag. One framing sees there being two major categories of evaluative visualization theories, those that are human-centric and those that are machine-centric. The machine-focused ones have long shown to have significant power, as tools like McInlay's effectiveness and expressiveness lend themselves directly to automation and mechanization, such as in recommendation systems. Yet, these theories are usually tied to preordained visual forms, or require complex and specialized software to employ, putting it beyond the reach of most practitioners. On the other hand, human-centric theories, such as Dork's critical InfoVis and D'Ignacio and Klein's feminist data viz, provides families of design principles, often phrased as questions, which can usefully guide the design process. This is great. However, these theories do not typically have a notion of correctness, and so can't actually judge quality and can be easily swayed by experiential or novelty biases. Now, this may seem to put us in a rough patch for pursuing theory-based analyses, but there's a sweet spot in this design: algebraic visualization design. Algebraic Viz, or AVD as I'll refer to it, was proposed by Kindelman and Scheidegger in their paper An Algebraic Process for Visualization Design, wherein they demonstrated how a designer could use their theory to identify and address weaknesses in visualization design. The basic idea of AVD is simple. It asserts that a change to the input of a visualization should be reflected by a corresponding change in its output. We can spell this out in a category theory style commutative diagram, which represents this assertion graphically. We model a change to the input as an alpha and a change to the visual as an omega. We assert then that these perturbations should commute. That is, a data change should be reflected by a corresponding visual change. Now, there are multiple ways that this assertion can fail. The first is called a confuser. This failure mode occurs when a significant data change yields an insignificant visual change. This slide shows a familiar idea, that aggregations can mask varied distributions. We can express this through the language of AVD by thinking of one of these scatter plots as the base data, and then each of the others as being the result of alphas or data transformations, and then observing that each of the scatter plots generates exactly the same bar chart, which we call a confuser. The other principal failure mode are called hallucinators. These occur when an insignificant data change yields a significant visual change. Dual y-axis charts are a classic example of this error, as arbitrary non-data choices can be made to produce radically differing outputs, and therein hallucinate meaning. Just as in this diagram from Lisa Roast, which shows the same pair of time series plotted according to 6 different axis selections, variously varying their relative scales and y-offsets. This demonstrates a hallucinator. This approach has been shown to be a useful ingredient in the design process, and it helps to raise issues and invalidate designs for particular tasks and datasets, pushing the designer away from bad designs. The way it provides these assertions are human operable and interpretable, while still possessing a clear definition of correctness. Correspondingly, several previous works have successfully explored mechanizing AVD to generally positive ends. And this is great, as it addresses many of the concerns we expressed about using theories in an evaluative manner. However, the usual response to an AVD error mode is to change the design until that error mode goes away, which is useful for a design process, but doesn't help us understand how to use a particular visual form. In this work, I introduce an extension to AVD called Algebraic Visualization Analysis, or AVA, which uses some of the mechanisms of AVD to ask and answer questions about a particular visual form of interest. The idea of AVA begins with the observation that there are 3 essential pieces to any visualization: the data, the way the data is encoded into a visual representation, and the task that a human does with it. Only by correctly pairing all 3 elements will a visualization be effective. For instance, a chart may be well matched with the data, but if that chart doesn't serve the reader's task, then it'll be useless. From this observation, and inspired by the very observed pattern from AVD, we can take a variational view of this triplet. We can fix data, encoding, or task, and then vary one of the 2 remaining elements to understand the third. AVD, as it's normally practiced, falls into this bottom regime, whereas exploratory data analysis fits into the top of this model by taking a data set as fixed and varying the encoding to see what can be done with the data. As we've already declared that we're interested in being able to evaluate a particular visual form, our work today will fit into this middle section. This prompts us to ask 2 questions. For a given visual form, what data can be used and which tasks are appropriate? These are both large and complex questions, so our strategy will be to break up each of them into smaller and smaller chunks till eventually we can answer them using AVD-style perturbations to identify AVD-style failure modes. The first step in this analysis is to pick a chart form. So we'll select a relatively rare chart called the table cartogram, or TACO, as I'll sometimes refer to them. Table cartograms are a specialized form of value by area map, or cartogram as they are more commonly known. TACOs were originally described by Evans and friends in 2013. They are similar to geographic cartograms in that they also embed data as area. However, they are different in that they have a grid-like topology and are constrained to a containing rectangle. That is, rather than transforming the size of states and countries, it instead resizes a grid of quadrilaterals to represent a table of positive scalars, yielding an effect that is similar to a heat map that has been areaed rather than merely colored, just as we can see here in this simple checkerboard table. Now, why do we actually care about table cartograms? Well, despite having existed now for 8 or so years, their functional properties are still unknown. The 4-ish previous works on this topic focused on developing layout algorithms without thinking much about how table cartograms would be used. We suggest that an aspect of their current rarity is contributed by confusion about how to effectively use them. Compounding this confusion is the fact that some surveys in prior work have identified them as being geographic cartograms. Yet, few geographies actually have a topology that is supported by the TACO's tabular form, and thus any mapping of such bodies require a hallucinator-inducing pre-step of forcing a geography into a tabular form. This all suggests that we have an opportunity to employ our analysis method to generate some new and potentially useful information. In addition, tacos are interesting because they contribute to the very limited space of tabular visualizations, which consists of a few common graphical forms, such as tables and heat maps, and a few more exotic forms here and there. This suggests that if we were able to find some useful applications and functions for tacos, then they'd potentially be able to contribute a lot to an underserved space. Now let's actually get down to our analysis. Answering the question of how do we use tacos is a big task, so we're going to break it up into stages per AVA, prepended by a brief warm-up. We'll start by looking at a prominent hallucinator. This is a table cartogram drawn from the original study by Evans and friends. It correctly encodes data as area, it maintains the planar topology, and is constrained to a rectangle. And here's that same data rendered using a different algorithm. It also has an accurate area embedding as well as an allowed topology and is correctly constrained to a rectangle. Both of these layouts are valid, yet appear to be substantially different. Unlike in tree maps, where algorithm selection has known and definite properties, algorithm selection for tacos has more ambiguous effects due to the variable shapes that the quadrilaterals can take on. This multiplicity of correct layouts is a hallucinator. For instance, a reader comparing two tacos of the same data prepared according to different heuristics may be deceived by their radically differing forms, unless there is, of course, a lot of signposting or the reader is especially careful. This suggests then that tacos are ineffective for tasks where concrete, consistent conclusions are necessary, in turn suggesting that they are ineffective for data exploration or analysis tasks. In contrast, this multiplicity can be a boon for designer freedom. A designer has a lot of room to make the presentation appear regular and ordered, such as on the bottom, or chaotic and irregular, as on the top. This suggests that tacos may be effective for tasks that involve the reader's awareness of the presentation medium itself, or more generally, for enjoy tasks. Next, let's consider what data can be used. This is a relatively large question, so it'll behoove us to break it up a bit. We'll do by asking about data type, data value, data size, and cardinality. We'll start by looking at data type. To do so, we'll need to build up a model of possible table types. Data tables, for the most part, can be defined by the meaning of their rows and columns. There are lots of ways to taxonomize data types, but a direct one is to use Stevens scales of measurements. These consist of 4 variable types, 2 continuous, interval and ratio, and 2 discrete, nominal and ordinal. Nominal values are those that are discrete and do not have an ordering, whereas ordinal are those that are discrete and do have an ordering. Continuous variables are either interval, which are those that whose y-intercept is not meaningful, such as latitude and longitude, or ratio, which are those that do have a meaningful zero, such as counts. We're interested in building a model of table axes, so we'll concern ourselves with just the discrete scales. We can assemble these into a space of possible tables. In addition to the Stevens data types, we can also form a sorted type by applying some sort to the nominal data. Now, our task is to look at each of these pairs and figure out whether or not there is an AVD failure mode, in this case, a hallucinator. Let's start by looking at a nominal variable paired with anything else. Here's a table cartogram describing the region-to-region migration in the United States during 2016. The rows are the from location, and the columns are the to location. So in the upper left-hand corner, we see that 580,000 people migrated from one part of the Midwest to another. Because these regions do not have an ordinal relationship, we can order them in any way that we wish. So this is a valid order, as is this, and as is this. Now, all that we've done here is we've applied a simple alpha, that is changing the order of the axes, couple of times. We see that this is a non-meaningful change that has a large effect on the resulting image. While the shapes are correct, they look quite significantly different under each ordering. This ambiguity is a hallucinator. Next, let's look at our special sorted axes. The idea here is to sort an axis by evaluating a metric of interest. Here we see 2 presentations of the same data where the rows are a nominal list of countries and the columns are an ordinal list of years. The rows on the left chart have been sorted in a manner that attempts to make the cells as rectangular as possible, while the presentation on the right have not. The idea was suggested by Inouye and Lee in their paper describing a method for creating table cartograms using an optimization algorithm. This sorting would appear to rectify the issue found in the nominal axes, as it creates a clear notion of how to present the rows and columns. However, this simply obscures the previous hallucinator. Without a lot of specific signaling, a reader might not know a graphic has been prepared according to one metric of interest versus another. If the reader uses the irregularity of the lines as a signal for disorder among the values, then that signal may be hidden or magnified by the selection of sorting algorithm. For this reason, sorted axes may carry a hallucinator depending on the context. Finally, we now consider the last option, the case of ordinal tables, such as in this multiplication table. As these tables are not subject to alphas related to reordering, we are unable to disqualify them based on the logic we've already been applying. Thus, we argue that there is no hallucinator for all ordinal data tables, although specific instances might have their own. This suggests then that the types of data found in CSVs and those whose meaning can be understood under multiple table projections, such as the tidy or widey projections, as well as hierarchical tables, whose organization is typically nominal, are not well matched with the table cartogram, while flat tables with ordinal rows and columns do appear to be well matched. The arguments for the other two lines of inquiry in our partitioning follow a similar reduce and reject pattern, so I'm going to gloss over them here, but the details of these arguments are in the paper. The highlights are that only non-zero positive scalars are valid, which should ideally be ratio, but interval can be okay too, depending on the task, although a pretty non-trivial hallucinator lurks in interval data. The size of the data domain should be smaller than 5 orders of magnitude, and in practice, we find that it's better to have them be smaller than 3 orders of magnitude. Similarly, we argue that the cardinality of the axes should be smaller than the number of pixels in the display, although this is approximate, as groups of cells can be viewed as visual aggregates, allowing for larger cardinalities, while large cardinalities might impede tasks like value lookup, which may or may not matter depending on the context. Having now seen what data can be used, let's see what we can do with it. We partition the space of possible tasks into manageable chunks by making use of Amar and Friends' low-level task taxonomy. While there are many other task taxonomies out there, we focus on this one because of its ubiquity and directness. Each task describes a low-level action a reader might perform with a visualization, such as finding a particular value, or identifying the data domain, which matches well with our reductive approach. We're just trying to get a flavor for this analytic mode, so we'll just look at a few key examples. Let's start with determine range, which asks us to find the magnitude of the minimum and maximum values. This taco shows Visitation Design National Park from 2007 to 2016 by month. Here is the data just as it is in reality. And here it is with all the values having been scaled by a factor of 10,000. This change is invisible. This is a confuser. In addition to suggesting that tacos are ineffective at determining range, this also suggests that only relative comparisons are useful for tacos as absolute ones are invisible. Next, let's consider retrieve value. Here I've changed a single value from the previous slide. Can you tell what that value is? Or even where it is? No, of course not. Because this too is a confuser and is totally invisible. This is in part because a change of a single value is not a meaningful change for this composition. Although, if that information mattered to the composite task that this elemental one was serving, then it would be poorly handled. In addition, this highlights the necessity of secondary encodings for table cartograms, for both this and for most tasks. Although it is notable that because of the coarse way in which we are applying AVD, we are unable to describe how they should be used, only that they are necessary. Next, let's look at how tacos handle find anomalies. Here we see the count of red light camera violations in Chicago during January 2016, dual encoded as a table cartogram and a heat map, where the numbers are the dates. We explore our task of interest by considering an alpha in which we set data outliers to the weekly average. This change is clearly visible, suggesting that tacos are not ineffective for tasks involving identifying outliers. A notable caveat here. The taco's irregularity can cause false positives when trying to detect outliers, as cells, which may have the same value, can be represented as quadrilaterals with greatly differing shapes. Yet, under an appropriate parameter configuration, as seen here, outliers can be seen clearly. In the paper, we work through each of these tasks and find that only find extremum and sort are always confuser-free, although some other tasks may be supported depending on the data. And this brings us to the end of our sample AVA style evaluation. And let's summarize what we've learned. Table cartograms are good for small data sets with ordinal axes, for some comparison and outlier tasks. They are not good for data analysis, but do seem to have value for data presentation. In tandem, this seems to suggest that they are well matched for casual consumption contexts, especially those that discretize time in some fashion, such as in calendars. The assertions we used to establish these results were relatively coarse-grained and left open questions that should be investigated in future work by experiment, such as the human response to tacos, or the effect that secondary encodings have on legibility. AVD is unable to reason about interactivity, so we ignored how interactivity might have affected these results. But future work might profitably combine the recent work on applying the Deleuzian fold to visualization and interactivity with AVD to consider these questions. Next, let's talk about what AVA is good for. While not able to address every concern, most matters related to perceptual quality being too subtle for the coarse way in which we applied AVD, it was able to help us build a coherent set of usage suggestions. Practitioners will continue to invent novel and visual forms, and we believe that discount evaluation tools, such as the one that we've exemplified here, will be invaluable to helping them determine effective practices. Of course, AVA isn't without its limitations. The divide and conquer style approach can only say that a property doesn't exist and not that it does, suggesting that AVA can only put an upper bound on visualization quality, as there might be a hallucinator or confuser still lurking in the visual form. Put it another way, tacos or any other graphic analyzed in this manner are as bad as we've described them to be, or worse. Now, throughout this work, we utilized AVD, which is desirable for lots of reasons, like we talked about. Yet it's not perfect. It's unable to reason about interactive or time-varying graphics. For instance, it would have nothing to say about hot plots. And its assertions are coarse-grained and can be overly simplistic, although, again, luckily in a consistent and directed way. And finally, the things that we learn from theoretical analysis are useful, but they don't establish ground truth in the same way that experiments do. Yet we believe that this type of theoretical work dovetails well with experimental work, allowing for the rapid exploration of possibility spaces, followed by confirmation of assertions by observation. This is just the first application of AVA, and in future work, I intend to more fully develop these ideas both by comparing them with other methods, providing a greater formalization of this machinery. So formalization may support mechanization of this form of analysis and therein allow for automatic analyses of novel graphics. Finally, here at the end, we turn again to the question in the title of the talk and give a slightly different answer. What are table cartograms good for? Evidently, they are good for an algebraic analysis. Thank you for your time and attention. Find out more about this work at this link, and feel free to contact me with any questions you might have.
Thank you, Andrew. Very interesting talk as well, and very interesting work. So we are ready to open the floor to the questions. And we have one question from Alexandra Dier. And Alexandra asks, I think that as soon as you work on the human social aspects, it will get very messy. Do you have any plans already about to handle the many nuances and subjectivity that would bring to the math model?
It's a really good question. And that is kind of the big question of visualization, right? That there is a messy human brain interpreting these graphical marks and channels. And so I think there is definitely work to be done, kind of trying to consider how theories like this and other ones like information theory kind of interact with humans, and the way that we sort of interpret them and like what value we can achieve from them. So as I go about kind of continuing to develop AVA and its various machinations and machinery, yeah, I definitely want to see what how people deal with these. That's definitely important future work.
Perfect. Also have another question, which is related to the strength of algebraic analysis. Do you think is it possible to apply the same theory to perhaps create visualizations for multiple tasks? That is, one visualization fitting more than one task.
That is an excellent question. Yeah, totally. Because of the really sort of physicsy style, reduce like hyper reductionist approach to everything that this approach takes, it totally does not think about mixed tasks. That's an incredibly good point. I had not thought about that. I think the way that it assumes tasks work is that they're additive, that you could, if that one thing works in one area, then it'll work in another area, but it doesn't necessarily look at their combination. Which I think is like an important weakness of any sort of really reductionist set of things. And we know that humans work in a Gestalt way, like the way that we understand things is holistic and rich, and kind of comprehension is an emergent property. And so taking this reductionist approach can be like, won't necessarily be able to say things about that sort of mixed task. So a possible approach might be to just reduce it again using a different taxonomy that uses the mixed tasks as primitives rather than these sort of more elemental ones.
Perfect. Thank you very much. We have one more question, which is asking, so it is not clear how we can automatically identify hallucinators in the visualization on a local scale for unknown visualization. So how do we apply your theory to new visualization forms, for example?
How do we apply our theory to the new visualization forms? Well, my hope was that this was an example of that. But I think the work is just to do it. There's just an element of experimentation that has to be done in order to sort of explore some of these. And you can also sort of just directly reason through some of these ideas. Like you can, if you sort of sat down with the definition of a table cartogram, you could just sort of like, make assertions about it until you got to your hallucinators. I think in future work, I want to make sort of the whole process more clear, so that it can be a little bit more of a turn crank affair, so that you can just you don't necessarily have to be as bold in your theoretical assertions, and you can just be like, ah, yes, here are the hallucinators, I have found them.
Fantastic. So we may have time for one more question. If not, I actually have a quick question, and I have seen algebraic analysis being linked a lot with information theory. And in visualization, we have a big bulk of work on information theory. I was wondering if you could see any link between your current work and some of the output that we have in information theory applied to visualization.
Totally. And I think that's really important in future work. I don't know what the answer is there. It's a really complicated question. My belief is that the next step in unifying algebraic viz with other things is sort of following Jessica Holman's assertion that Bayesian model checks are a good way to do graphical inference. I think that there's a pretty rich connection between that and algebraic viz, yet to be sort of like specifically and fully enunciated. But I would suspect that kind of the properties of information theory and like information theory viz therein are kind of wrapped up in that as well. Like I think that there is sort of maybe a grand unified theory of visualization theories out there. It's hard to say if such a theory of theories would actually have concrete meaning on physical reality, given the meat brains. I think it would be interesting at the very least. And it remains for experiment to determine if that would be useful.
Perfect. So thank you very much, Andrew. So I think we need to wrap up the session to leave time for a break before the keynote, the industrial keynote talk starts. So I would like to invite everyone to give another round of applause to our presenters. And we also, I think also on behalf of the other paper chairs, we would like to mention how this piece of work, actually to borrow a comment from the audience, how they showed some really bold work, and which we hope will generate a very live discussion. Nevertheless, also the papers that are coming up in the next session are all extremely interesting. This year we had a really strong pool, so the selection was also very, very challenging. And we would also like to thank our technical support and our student volunteer that helped us in filtering out also the questions and keeping 3 different streams going on. So thank you very much for your presentations, and we wish you all to enjoy the rest of the conference. Thank you.